All right, well, welcome and thank you everybody for joining us for today's C2 Smart webinar, which is the first of a summer webinar series presented by the Transportation Research Board Subcommittee on Route Choice and Spatio-Temporal Behavior. I'm Elizabeth, or Lizzie, and I'm a research project manager at the C2 Smart Center, which is a US DOT designated Tier 1 University Transportation Research Center tasked with leveraging recent advances in big data and technology to solve today's most pressing urban mobility challenges. And today we are joined by Professor Mogens Fosgerau, who will present on the perturbed and utility route choice model. So some quick notes to start. We'll be recording this session and then uploading it to the C2 Smart Center YouTube channel. And I also want to encourage everybody to participate through posting questions to our presenter and our panelists today. You can do so by pressing the Q&A button at the bottom of the Zoom window, and then we will read out the questions at the end of the presentation. Today's presenter is Professor Fosgerau from the Economics Department at the University of Copenhagen, and his areas of research include microeconomics and econometrics applied to problems in transportation, and particularly to issues concerning time, reliability, and congestion. And with that, I will hand things over to the professor to carry us forward.
Many thanks. Thanks for the invitation to do this seminar, and thanks to everybody for joining. So I'll try to introduce you to the perturbed utility route choice model, which is a model that so far has been presented, introduced, and used in two papers. They're both open access. The last mentioned first here just came out in PNAS. It's about bicycle infrastructure, where we use the perturbed utility route choice model. And the model itself was introduced in this paper from last year in Transportation Research Part C. So they're open access. So I hope somebody would be motivated to read them, So where this research begins is that we're getting more and more data that trace vehicles or bicycles or buses or passes or whatever through large networks. So now we have much more data than we had some years ago. Maybe even so much data that it's hard actually to use it without changing the way that we do models. And then, as many of us know, I guess, working with large networks, we are facing a curse of dimensionality, that the number of routes connecting any 2 points in a large network is extremely large. So that gives us some issues, and it gives us some problems with obtaining realistic models, because we would like to have models that respond in a plausible way when we change the network in some way. So what we are doing here is that we'll come up with a new kind of route choice model. And it's a model where, as the old models that we're used to, they have utility maximizing travelers that choose the optimal route for them. In the new model, they choose a flow. So in a way, it's a flow choice model rather than a route choice model. But the new model allows us to take the complete network, whatever it is, into account. So we don't have to deal with choice set generation or anything like that. We can just work with the network as it is. The model has a correlation structure. It induces a correlation structure just from the network. So we don't need to do anything special to have the model produce plausible substitution patterns. They arise naturally. And another feature, as we'll see, is that the model produces as the predicted behavior that for every OD only a small set of routes will be active. And then what makes it all work is that because we have formulated the traveler's utility maximization problem, we can work out the optimality conditions for the traveler and base our statistical inference on that. And then, as you'll see, it's possible to transform those conditions into a plain regression, which means that this model can be estimated just with linear regression really, really quickly. So we can handle lots and lots of data, real networks, and estimate models in seconds. So I'll begin with some background, outlining the state of the art, very briefly, of course. So I'll miss a lot. It's a big literature. So what we're looking at is models that predict the distribution of traffic flow in a network, like the one shown here. Maybe I hope you can see it on your screens. That this is a very detailed network that we're looking at. So it's actually Copenhagen. And then we're looking at predicting how people come from some origin to some destination, how they travel in such a network. And clearly, there are very, very many ways to get from O to D in such a network. If we allow loops, which we might want to do because loops are possible, so we don't want to rule loops out ex ante. It should be a result of optimizing behavior, not an assumption that we impose beforehand. Then there are infinitely many routes between any OD in any OD. And even if we rule out loops, there are extremely many routes, so about as many as there are atoms in and on Earth, which means that there's no way we are going to list all of them on any computer. It's not possible, and probably will not be unless we go into hyperspace or something. So it's just not possible to work with the choice set in a discrete fashion as we normally would when we use discrete choice models. However, it has been what has been possible. It has been the tool that we've had available. It has been the logic model and descendants of Perturbed and descendants of that, which means even though this problem, the root choice problem, is not that well suited for discrete choice model, that has been what we have had available. So therefore, the problem has been necessary to reduce the problem to a size that we can actually handle with standard discrete choice models. And that means we have to look at only a small set of possible routes, which means we have to we run into problems with observed routes that are not allowed in the model and biased parameter estimates and so on. So it's not ideal. Another issue that we face is that as soon as we split everything into path alternatives, then we're sort of separating the different routes, making them completely different. But then we want to introduce correlation back into the model to take into account that some routes, like the blue and the green here, are much more similar than, say, the blue and the orange route. So we want to handle that routes have more or less in common, which induces correlation in route choice. And that, unfortunately, turns out to be quite hard to do in a satisfactory way with the classical discrete choice models. Then we have another kind of model that I have also been working on, which is the family of recursive loaded models, recursive nested loaded models. There's several variants, which is a link-based model that sort of is in a way it's new. So what we did that was new was that we've found a way to set it up where we could estimate such a model based on observed root choices. And it's link-based, so it takes the perspective on a root choice as it's step by step, link by link choice of the next link. And the way that's done is as a dynamic discrete choice model, where the expected utility associated with arriving at the next link affects the current root choice. And that can be, so that means it's necessary to solve and find the expected utility of arriving at any node in the network, which is a fairly large computational problem, which means that it's limited how large problems we can actually deal with in practice. Otherwise, it just becomes too slow. So we are limited in size with in the size of the problem we can handle with the recursive loaded model. So that's the background against which we introduce this new model. And it comes from a paper that I did with Dan McFadden that we never managed to publish, actually. It came out as an NBER working paper, and that's how far we got. And the trouble that we ran into with referees was explaining how this kind of theory was useful. So now I can say it's useful for root choice and other things, but at the time we didn't manage to convince the referees. But basically, it's a very, very simple model, because it just says that a consumer has a utility, and the behavioral assumption is that the consumer is utility maximizing, subject to the consumption vector X belonging to some budget set. And then what makes the whole thing work is that we are assuming this functional form for the utility function, that it must consist of a linear part. So we have sort of sub-utilities associated with the different products that we imagine in this model, inner product with the consumption vector, and then minus a convex function of the consumption vector. People in OR know a lot of convex analysis. They would recognize that the utility maximization here is the same as computing the convex conjugate of F. So there's a lot of math that becomes available just from noticing that this just fits into convex analysis. And then later it has turned out that this general model generalizes a range of different models. So the standard consumer theory model, which is just concave utility, so that's minus a convex function, fits into this framework. Budget is so the cost of consumption should be less than income. The additive random utility model fits into here. Bottles models fit into this framework, choice under risk, stochastic choice, and so on. So that's a paper by Allen and Riebeck. They show that this is a model that generalizes practically all the models that are used in microeconomics. So now we take this general framework and specialize it to root choice. So the consumption vector is going to be a flow vector. So that's the vector that assigns a non-negative flow to every link in the network. And the budget set is says just that there has to be flow conservation. So the flow into each node has to equal the flow out of the node, except for the origin and the destination. And as we'll see, then we can deal with the main issues that we have with sort of AROM-based models. So in more detail, it looks like this. So the flow vector X is specific to an OD, and it's a number for every link in the network, every edge in the set of edges. Utility has a part here. So we have a utility for every link that we're going to parameterize as parameters times link characteristics, times the flow in the link, minus a convex function of the flow in the link for the flow originating from the OD that we're looking at, then weighted by length and summed across links. And here's the conservation constraint. So it's a specific instance of the general perturbed utility model where the consumption, the analog of consumption is a flow vector. It's important, this perturbation function that we have. So it has to be strictly convex, strictly increasing, has to be zero at zero flow and flat at zero flow. And that is going to be important for how the model works. So it can look like this. So this one is the formulation that we're actually using so far, but we could just use the quadratic. So they are, and there are many possibilities for coming up with functional forms for F. So we can just choose something convenient, and maybe in the future there'll be research to guide which forms are maybe better than others. And what it does, this perturbation, if I just go back one slide, if the perturbation function was not there, then the utility optimizing flow would be the same as the cost minimizing flow. It would just identify the shortest path. So then, if F was just 0, the model would predict that a traveler in some OD would just choose the shortest path. However, with this convex function, we can imagine that we turn up the flow from 0, and then this part begins increasing up from 0 at the active links. At some point, there will be an alternative path that will become the shortest path. And then that path will become active as well. So these two paths, they may overlap a lot or a little bit. It depends on the network, but then there'll be two active paths. And then the convex perturbations, as we increase the flow even more, will also increase to the point where a third path may become active, and so on, until we have assigned a unit mass flow to the network for this OD. We can interpret this perturbation thing in different ways, but it's essentially what it does is to distribute unit flow from origin to destination on several routes, on an endogenous number of paths that are the shortest paths, not just one, but some number of shortest paths in the network. So here's an example of what it can look like. So these are the paths generated by the model in Copenhagen, going from the airport to the technical university. So we see, so for those who know Copenhagen, this is reasonable. There's the ring road or different ways to go through the city center here. So the routes are not silly, but they're it's a fairly small number of links from the network that are actually active. So the model finds a small set of links that are active, but I don't know how many routes, how many paths there really are. Maybe, I don't know, 100 or something. But that's what it looks like. So out of the extremely large number of potential paths, we get like a very small number. And this is with the whole network available. So nothing has been ruled out ex ante. Everything is guided just by this Perturbed utility function. So we don't need to have predefined routes to choose from, predefined paths. Because the way the model works, that the active paths are the k shortest paths, and where the number of active paths is endogenous. So we get from the optimality conditions that these active paths all have the same marginal utility or the same marginal cost, which means going this way has the same cost as going, say, this way from the origin to this section. They're all so increasing the flow on any of these paths will cost the same in utility terms. And that means that if we think about changing the network somewhere, as we have an experiment in the paper, like here, maybe we introduce a toll on this bridge, then the way traffic will shift, the flow will shift, will completely follow so from the network structure, because what the flow that we will end up having after the toll or whatever that we change the network will still satisfy this optimality condition that all active paths have the same marginal utility. So that means we get in a completely straightforward way plausible correlation patterns, plausible substitution patterns. And we can compare that to the different methods that we have for introducing correlation in this sort of discrete choice AROM-based models. So let's talk about how we can estimate this new model. And it's not, so we have to go through a few steps before we end up with an equation that can be estimated. So from the utility maximization problem that we saw, we can find the first order conditions for utility maximization, and they look like this. So there's one. So the first says that either for every link, either the flow should be 0 or the first order condition for interior solution should be satisfied. And then we have a lot of Lagrange multipliers here. There's one for every conservation constraint, which means there's one for every node in the network. So in the Copenhagen network, that means we have maybe 30 or 50,000 Lagrange multipliers, which is too much to estimate if we wanted to try that. So we want to get rid of these Lagrange multipliers, and we also want to get rid of the zero links because we want to use the interior solution condition as a basis for setting up a regression equation. So the first step in getting something that we can use is simply just to remove, for some specific OD, just remove all the links where we observe no flow. And that's okay, because so the flow that we observe is stochastic, so we may have observed a zero on some flows, on some links that have a positive probability of being used, but we see for sure only positive flow on links that are actually active in sort of satisfying the interior, the condition for interior solution. So if we observe a positive flow, we know that the condition for an interior solution applies. So we can form a matrix which is just an identity matrix, but with rows removed for zero flows, where the flows are zero, and then just multiply the first order condition for that, and then we get rid of the part where that allows the link flow to be zero. So now we have just a linear equation, which takes us some of the way where we need to go, but still we have all these Lagrange multipliers. So to get rid of them, we use the Moore-Penrose pseudo-inverse, which is of this thing here. So A is the incidence matrix for the network, and B is the matrix that removes the zero links. The pseudo-inverse of that matrix satisfies this equation, so we can, yes, which looks like this. And that's useful because if we take the first order condition that we arrived at and pre-multiply by this thing, then we get, here we have here, and here, we have the first order condition as it looks now, pre-multiply by this bit, but here with the Lagrange multiplier, we get this stuff that reduces to just this stuff. So we can isolate and get an expression for the Lagrange multipliers multiplied by this matrix in terms of things that we sort of know, the link utilities and something based on the perturbation function. So if we know the flow and utilities, then we can compute this transformation of the Lagrange multipliers, and then substitute back into the first order condition to get rid of the Lagrange multipliers, and then rearrange to get something where we have some transformation of the observed flow equal some transformation of the link utilities. And if we then specify the link utilities as some parameter beta times a vector, which is all this, and which includes the network characteristics, then we can So we get an equation like this, where we can just add an error term, and then we have a regression equation. So we can transform, if we observe flows or something approximately equal to the predicted flow, and we observe the network characteristics and form linked utilities like this as a linear function of link characteristics, then we can set up a regression equation that allows us to estimate the betas that determine the linked utilities. So we have one final problem to deal with before we can actually do it, which is when we have observed trajectories, then they have origins and destinations all over the place. So even though we have very, very many observations, we will have very many unique OD combinations. And that's, we need multiple observations using different paths for every OD to compute this thing here. So we have to observe approximately a flow vector and not just one path. So what we do, and this is the main cost so far in using the new model, I guess, is that we need to pre-process the data, sort of trimming trips such that we get origins and destinations that are common to many trips. So we have an algorithm that does that. So there's some pre-processing that's necessary. So we can see how it works. First, the first paper that we published, we used GPS data for cars. So we have 1.3 million trips and 8,000 active ODs. And not so many variables that we can use to explain the route choices. So we have the average observed travel time per link. We know the link types, what kind of road it is. And we use a variable that counts the number of outlinks from every node. And then we estimate three models, one where we just have a parameter for travel time, one where we add a constant penalizing more than two outlinks, because then there's an intersection, and then a model where we include dummies for different road types. And I don't have time to talk about all the estimates, but what we should notice is that we get very, very high precision. We get, when we look at the predictions that we get out, if we apply the model with these parameters, they look plausible, and we get plausible differences in the dummies for the different road types. So as far as we can tell, these estimates are reasonable. They seem realistic. We can test how well the model fits the data different ways. One way to test it is to compare the flow that we predict on every link to the observed flow on every link, aggregating across ODs. And the perfect model would give us something that's just on the 45-degree line, and we get something that's close. But given that we have, I don't know, 50,000 links or something in that neighborhood, a wide range of observed flows, and just 9 parameters in the model, I think this is pretty good. We also did an out-of-sample prediction test, and it looks more or less like this. So, so I think the fit is convincing. Another way to look at how well we do in matching the data is to show the correspondence between observed and predicted flows on the map. Blue links are links that we predict accurately, more or less, and that is so the blue network is more or less the main road network in Copenhagen. Links that we do not predict so well tend to be minor roads. So it's not perfect, but it's pretty good considering that we are estimating everything in the whole network with 9 parameters. Another way of evaluating the model is to ask whether, or to which extent, the links that we have actually observed flow on are the links that the model predicts to be active. If this was perfect, then the proportion of utility that we observe outside the predicted set of active links would be 0, and it is 15%. But as almost all observed trips have less than 20% of utility outside the predicted set of active links. So we're doing pretty well, and as we can see. So that was the car application. Then in the PNAS paper, we have an application to bicycle data. So in Scandinavia, there's a kind of bicycle helmet that's not a helmet, that's pretty popular. So it's an airbag that is worn around the neck, and if it is, we have to hope it works, but it usually does. So if there's an accident, then the airbag inflates and protects the head. And with that comes an app that people can choose to use, and they can allow the data to be recorded and used for research. And that's what we've used. So we have 200,000 trips, bicycle trips in Greater Copenhagen recorded by the GPS in people's phones from 5,000 users. And then we've chosen only to use trips that are at least 1 kilometer long, and map matched them to a very, very detailed network. So more detailed than the car network, because now we have every little bike path, pedestrian paths, so everything that is relevant for bicycles, not just the roads, but many other infrastructures as well. So this is all of the data, that the map match data that we see here. Then again, we need to trim the trips because we need to have common O's and D's. So we select 200 origins and 200 destinations as candidates, and then have some algorithm where we trim trips until we, so in a way to retain as much of the data as we can. And we end up with having 150,000 trimmed trips that we can use in 12,000 ODs. So that's the effect of trimming. So we retain most of the bicycle kilometers, but we lose most observations away from the center where we have few observations. This is just a fact of life, but it's not desirable. Of course, we would like to have an even coverage of the whole network, but of course, there's more traffic in the denser part of town. Then I don't have time to go through the model in detail, but I just want to show you that there is a lot of detail in this model. So we have a lot of detail in the data, and we can handle it with the model. So we have 16 infrastructure types, 6 land types, blah, blah, blah. So this is a list of all the variables that we include in the model. And the main thing to notice is that it's very long. Here's the fit that we obtain it is as good as what we saw for cars. And this is the parameter estimates that we get. And we notice again that most parameters, not all, but most, are very precisely estimated. I think everything, at least more or less everything, that all parameters make intuitive sense, the relative sizes make intuitive sense. So I put them on the slides so people who want can read it later, but I won't talk about everything here. So now it's all recorded on the video. So one potential use for the model, which could be nice if somebody wanted to do that, is that we can draw the estimated cost rates or utility rates link by link on a map. So green is good, that's low cost, and red is bad, gray is in between. And then maybe the municipality would like to look at this map and see, here, maybe there's something missing here. Here we have a gray area. Maybe it's it could be worthwhile to put a backlink here. So that's an easy way to identify candidates for improving the infrastructure. I'm running out of time. So very briefly, we can put a gravity model on top of the root choice model and estimate a demand curve for or a distance, kind of a distance decay from the gravity model, but based on the cost from the root choice model. And have so more or less non-parametric estimate of the decay. Looks like this with confidence bands. And then we can do counterfactuals where we experiment with changing the network and see what happens. So these are then, if you can see, the network changes that we've looked at. And for today, it's not. So the main thing is we can do this kind of thing and compute counterfactual scenarios and do cost-benefit analysis corresponding to those, and say things about what is the benefit of the infrastructure that we have, or we could compute the benefit of new infrastructure. So in conclusion, we have this new model. Does not require choice set generation, allows lots of zeros. The network structure induces correlation, and it's really, really easy and fast to estimate. So we can try out lots of models. We can have demonstrated that we can use it with real networks and with very large databases of observed trips. And we can combine with a gravity model that tells us how much traffic we can expect in every given OD. And I hope this is just the beginning. I think that there's much more that can be done with this kind of model. And it's relevant because we are getting these data sets now. We have network data that describe sort of most cities in the world, actually, in very great detail. And now we have this new way of modeling things, where we don't think in terms of probabilities for discrete choices, but we think in terms of flows across networks, which is a generalization of the discrete choice perspective. And the main thing that we would like to do is to not have to trim trips. We would like to be able to retain the full granularity of the trips that we observe in combination with the full granularity of the networks that we have. And then combine, which is, so the connection with the gravity model so far is a bit ad hoc. It would be really nice to have an integrated theory. So there's much that needs to be developed in terms of estimation using individual level data, understanding the analytical mathematical properties of the model, how to compute predictions efficiently, how to compute equilibrium assignment. So that's all. Thanks for listening, and I look forward to the questions there might be.
Thank you, Professor. And as a reminder, we do welcome questions, so please enter yours by pressing the Q&A button, which is at the bottom of the Zoom window. And we're also joined today by Professors Joseph Chow from NYU, Natalia Barber from the University of Central Florida, and Roger Chen from the University of Hawaii at Manoa, who will help with questions and provide some closing remarks.
Yeah, thank you, Lizzie. So I'll just kick off I want to thank Professor Fosgerau for this inaugural talk in our subcommittee's summer webinar series. As for those who might not know, this is a joint subcommittee at TRB on route choice and spatial-temporal behavior, and we're part of both the network modeling committee as well as the committee on travel behavior and values. So I'll start off with a question, and maybe Roger might have a question as well afterwards, and then Natalia will help handle some of the questions from the chat that will come in. So I want to start off with just in terms of the model, you're estimating the parameters based on the flow. So I was wondering how you would take into account, let's say, background traffic, as well as uncertainty in the origin destination demand values.
That should be on the to-do list, I guess. So I don't have a way of doing it. Well, background traffic should be in the travel times that the individual is facing. So if we can handle that so know what the observed travel times, or what the travel times are corresponding to the flow observations that we have, then we're fine. But that's a problem in itself, common to this model and the classical discrete choice models. So uncertainty in principle, we should just do as a first approximation anyway, do expected utility. Right? I don't know how easy that is, but so I haven't really looked into it. But it's certainly very important to take it into account. So one thing we could think about is well, just there's uncertainty, and then which can be handled as part of utility, or it could be handled maybe with rational inattention, so there's a little bit of work. I've done a little bit of it myself using rational inattention models for route choice with path-based models. How it will work out in this context, I have no idea.
All right, thank you. Roger?
Okay, yeah, so thanks for the wonderful talk. So how are individual characteristics incorporated in your model? Because it's based on link flows, right? So
Yeah.
if we had some attributes of the cyclist, maybe their experience, how would that factor in?
Yeah, well, so far we didn't do it, except we are dividing, segmenting observations by OD, and computing a flow vector for every OD from the observed data. If we knew background information about people, then if we had enough data, we could just segment on that background information as well, and add parameters to the model, interacting background characteristics with network characteristics. So in principle, it's easy. In practice, we probably run out of data a bit, well, too early, and if we manage to go to the individual level, on the other hand, then it's in estimation. So it's so we can base estimation on individual observed paths. Then I guess it's not a problem to include all the background information that we might have. And I think that will be really important when we get to look at things like road pricing, where people have different incomes and therefore will respond differently to road pricing.
Thank you.
Thank you so much for the talk. And we have a few questions coming from the chat. The first one is from Emma. Can you talk a little bit more about the structure of the flow prediction problem and the computing time?
Yeah. So when we did these papers, the flow prediction problem, we used something called MUSEC, which is conic optimization, which was feasible but took some time. So we can, I don't know, maybe do one OD in a second or something on a standard PC. It's something I'm working on with some other people at the moment. So I think we have something now that's a lot better, but still work in progress. So we can do it much faster. Still using the structure of the problem, and using as when we finish the work and publish the working paper, what it will be that we can partially solve the problem and reduce it to a problem that's fast to solve or faster to solve numerically. And this will be really important, I think, for going to the individual level, where we need to compute predictions, I guess, very many times. So we need the speed, the computational speed there.
Thank you. We have 5 minutes and a couple more questions. The first one is from Scott, who's asking a little bit more regarding the interpreting of the perturbation function to correlation or substitution in the discrete choice models.
Yeah. So what can I say? Maybe it's nice to go back to a picture, if the computer allows me. Yeah, something like that. So, so on, say, this route, there's a number of links. I don't know, 100 maybe. On every link, there's a cost that enters the linear part, and then there's the perturbation function. The perturbation function is specified. There's one convex f for every link, but but it's weighted by the length of the link, which means that if we split a link into two that have both have half the length, nothing changes. Okay, so it's so the prediction is invariant to that kind of thing, and that's regardless of which perturbation function that we might want to use. The first order condition says that for every, so in a way to look at it is that the marginal cost, so that's the derivative of or the fs, or the convex perturbations summed over the whole root, plus the cost of the root from the linear part they should all be equal, because otherwise, if there were differences, then the traveler could increase utility by moving from the more expensive route to the less expensive route. But the cost that is relevant here is including this convex cost function. So it's not so we don't expect to identify this thing in the brain or anything like that, but it plays a similar role to the random error terms in the discrete choice model. So they seem concrete, but actually nobody ever saw an epsilon from a logit model. We never observe utilities, so we never observe the epsilon. So these are completely hypothetical constructs that have the function of making seemingly identical people distribute on choice options. And this function, the convex perturbation function, does the same job, just not with random error terms, but with a dual representation of that, actually, in this dual in the sense of convex conjugation. So it's just another mathematical perspective on the same thing. It does this same job, it has the same function.
Thank you so much, because we're almost approaching 1 o'clock. To be respectful of everyone's time, I'll have to skip the other two questions in the chat, or maybe perhaps the participants could email you the question that they asked, and I will hand it over to my colleagues to conclude the webinar. Thank you again.
Okay, I guess I'll close out. So thank you everyone for attending our first webinar of our webinar series for the summer. Just a sort of reminder for everyone, we have 2 more speakers lined up in the summer, and the next one will be Marcela Minazaga from the University of Chile. That will happen sometime in the middle of June. And also just, reiterating what Joe had said, this is sponsored by the Subcommittee on Root Choice and Spatio-Temporal Processes. Our parent committees are AAP 30, which is Traveler Behavior and Values, and AAP 40, which is Network Modeling. And I think with that, we're good to close it here. So thanks again, everyone. And then if you have any questions about the series, please do email either Joe or myself or Natalia, and or if you want to be involved in our subcommittee. And let's thank Professor Fosgerau again for taking his time to speak to us on this very fascinating topic. All right. Okay. Thank you very much.
Thank you. Thank you for being here.
Thank you.
Thank you to all participants and attendees for joining today. And as a reminder, a recording of this webinar will be made available on C2 Smart's YouTube channel and website. All right, thank you all again. Have a good one.
Great. Thanks, everyone. Bye.